So today we're going to talk about functional groups, and functional groups are a set of atoms with a specific structure that impart a certain reactivity or physical properties to a molecule. So I'm going to use a shortened table compared to the one that's in Klein, but when you do your memorization, and you should make note cards with the functional group structure on one side and the name on the other, and be able to easily identify each functional group in a larger molecule by its name from memory. So please start going on those functional groups, but use your table from Klein, not this one that's shorter. So in this group, or in this table, you can see that in the upper left-hand corner, there are 3 types of functional groups that are just composed of carbons and hydrogens, and those are hydrocarbons, but the double, triple bond, and the benzene ring or aromatic imparts specific reactivity that sp3 hybridized carbon containing hydrocarbons don't undergo or don't have. Then you can roughly group the alcohols and the ether and the amine. It's kind of an exception with what I'm going to say with the phenol and the phosphate ester, but a rough idea of these are it's sp3 hybridized carbons directly bonded to an electronegative element. The phenol and the phosphate ester, like I said, are going to react a little differently, but just in general, these are that carbon singly bonded to a functional group. And so these are polar covalent bonds. They form hydrogen bonds because you have that electronegative element directly bonded to a hydrogen. And so they're going to have kind of relatively high boiling points and melting points, especially compared to these hydrocarbons up here. The final group that I just want to point out for now is these carbonyl-containing compounds, and a carbonyl is a carbon doubly bonded to an oxygen, and so aldehydes, ketones, carboxylic acids, esters, amides, those all have that polar carbon-oxygen bond, and so electron density is being pulled away from the carbon by the oxygen, giving that carbon a partially negative charge, and the oxygen a partially negative charge. And so all of these have a special reactivity that we'll look at predominantly next semester. These are the molecules that really control how biomolecules like proteins and DNA, how they function and what their structures look like. And so these are really relevant to biology. So that's something to look forward to next semester when we look at their reactivity. So one of the things that you should be able to do is look at a molecule and identify the functional groups that are in it. And so for instance, we have an alcohol and an alkene over here to the left. Sometimes you will notice that there are these, we call them wedge bonds or dash bonds. Wedge means that the carbon at the end of it, or the hydrogen or the oxygen, is coming towards you. Remember, these carbons are tetrahedral, and so they can't all be in the plane of the page. So what that means is that this is meant to be coming towards you. The dash over here, or bonded to the hydrogens, means that those atoms are going back behind the plane of the page. So when you draw your bond line structures, you do need to remember to add the hydrogen when it's directly bonded to an electronegative element or non-carbon element, as you can see here. And then down here at the bottom, you can see some of those bond line or skeletal line structures drawn out compared to their Lewis structures above them. So one of the things that you'll see in drawing functional groups is that very seldom are lone pairs actually shown. And so you want to be able to look at the formal charge of a functional group, or a carbon for that matter, and be able to mentally add the lone pairs. So you can see that with this little watch out box. formal charges must always be drawn. So you don't forget to draw them. They should always be drawn or written in right next to the atom that's charged. They can't ever be omitted, but lone pairs are just kind of slow to draw, so we often don't do that. So here's an example of some structures where we have a we have a negatively charged. Let me find that. There we go. Okay, we've got a negatively charged oxygen, a neutral oxygen, and a positively charged oxygen. And if we look back at our previous screen, maybe if I can get there. Oh, come on. There we go. Let's try that again. Come on. It does not like me right now. Hold on. Okay. Got there. Okay. Sorry about that. So if we're looking at the oxygen atom here, if we have a -1 charge, then there is 1 bond and 3 lone pairs. For neutral oxygen, it's 2 bonds and 2 lone pairs. And for a positive formal charge, it's 3 bonds and 1 lone pair. And there's not any choices there. If there's 1 bond and 3 lone pairs, then it has a formal charge of -1. Like there's no other choice. So if we go back over here, we see that there is a negative charge, and so that 1 bond is already being shown. And so you would need to put in the 3 lone pairs. Neutral, we have the 2 bonds shown, and so we would need to put in the 2 lone pairs. And here we have the 3 bonds shown, so we need to put in the 1 lone pair. And if I can do it quickly, I will. We'll see how it goes, though. I haven't been having very good luck with my pointer here. Okay, so let's see here. 1, oh, there we go. Okay, it's going. 2, and then my 3rd. Okay, up here we have our 2, and then we have the 1 down here. And you don't have to actually show those lone pairs unless it's specifically asked for, or you'll see when we draw out reactions that it's often useful to use and draw in the lone pairs because we want to show what they do over the course of the reaction.